Thank you so much, Deputy Vice-Chancellor. Deputy Vice-Chancellor, honoured guests, colleagues, ladies and gentlemen, this week the university celebrates the launch of its newest institute, the Aerospace Systems Research Institute, or ASRI. ASRI is committed to the development and commercialization of advanced aerospace technologies. Our primary goal is the development of a commercial satellite launch capability for South Africa. And in plain language, what that means is the ability to launch commercial satellites, both South African satellites and those of foreign customers, to low Earth orbit on a South African vehicle from South African soil in a repeatable and financially sustainable way. So during this week, we are going to be hosting a series of events. Those include a research seminar for postgraduate students and a STEM event on rockets for local schools. But this evening it is my privilege to kick things off, start the ball rolling, I guess you could say, with this talk, which we've titled Forging an African Space Launch Capability, the story of the Aerospace Systems Research Institute. So let's get started. For an institute to function effectively, it has to look beyond the boundaries of its host university to the broader society. And for an institute that has commercial ambitions, as ASRI does, it's important for us to understand the global space economy before we attempt to supply technology solutions into that economy. So we will begin there. And in that process, I will attempt to make the case for an independent South African rocket launch capability. It's not possible to have a lecture about rockets without talking about rocket science. And so for a brief detour, we'll look at these mighty machines, how they work, and some of the challenges associated with designing and building them. A rocket by itself is not a launch capability. There is an entire ecosystem of technologies and capabilities that have to be developed alongside the vehicle. And so after looking at the space launch ecosystem, I will introduce more formally ASRI to you, our origins and objectives, what we're all about, and our people. And then for most of the talk, we will focus on the technology programs that ASRI runs in order to achieve our goals. The reason there is a space economy in the first place is because of the utility of satellites. There are not many people who build rockets for the sake of building rockets. They all do one fundamental thing if they're orbital vehicles, and that is they place satellites in orbit. And you might be wondering why there is a demand for satellites. And I put it to you that our modern lives depend increasingly on spacecraft, perhaps in ways that you have not imagined. I will give you two quick examples. The first is satellite television. I'm sure that many of you on a regular basis watch satellite television. In South Africa, that would be DSTV. That signal that comes to your decoder first travels from the ground to a satellite. It's an Intelsat satellite stationed at nearly 36,000 kilometers above the surface of the Earth in what we call a geostationary orbit. It travels at about 11,000 kilometers an hour, and it was placed there in 2012 by a European Space Agency rocket called Ariane. If you don't want to do without your satellite TV, then you need to acknowledge the role of satellites. How about Google Maps? I'm quite sure that in the last week or 2 weeks or perhaps month, every single person here at some point, if they have a smartphone, has used that smartphone to get directions. Well, your smartphone uses the GPS system, which is a constellation of satellites located about 20,000 kilometers above the surface of the Earth in what we call a medium Earth orbit. And those were placed there by a variety of rockets Atlas rockets, Delta rockets, and more recently by Falcon 9 rockets. And I could give you a whole lot more examples, which I've noted there on the screen, of ways that our lives are dependent on satellites. When we communicate, in many cases, our communication goes through satellites. When you withdraw money from an ATM, the chances are, if you walk outside and look at the outside of the ATM facility, you'll see a satellite dish that is communicating back to your bank off a satellite. Weather prediction, looking after the environment, monitoring for disasters, water management, crop management, improving crop yields. The applications are almost endless. So at the moment, there are 10,000 satellites orbiting, active satellites orbiting above our heads. And every single one of those got there on a rocket. There is no other way at the present time to get a satellite into orbit. So before we look more at the value of the space economy, I want to just point something out, because there's been a radical transformation of the space economy in the past 30 years. And if ASRI aspires to supply technical solutions to that economy, this is something that we have to be cognizant of. So if I talk to you about the space race, most people know about the space race, but they imagine that space race to be the old space race between geopolitical rivals. So the Soviet Union, America, 1950s, 60s, 70s, all the way up to the 90s, the space launch industry was dominated by that particular mode. And even if you were launching a commercial satellite, the chances are it was going to go to orbit on an Atlas or Delta launcher, maybe on the space shuttle. But the early rockets, including the Atlas and Delta and many others, including all of the Soviet rockets, are actually repurposed missiles. They were born of the Cold War. And then sometime around the mid-1990s, NASA decided, the US government decided that it was important to change the way people and goods were delivered to the International Space Station. So they implemented a program which was initially called Alternate Access, and later the Commercial Orbital Transportation Services Program, or COTS. And they incentivized companies to build rockets instead of the old familiar defense industry. And all of a sudden, old space turned into new space. So what is new space? It's about being driven by commercial interests. It's about private entrants developing a host of new reusable rockets, not the old expendable types, but rockets that you can fly and put back on the pad. It's about agile business models. It's about fast and innovative manufacturing techniques. And above all, it's about something that I've called fearless innovation. In the old space setup, because companies were involved with governments and because of the inevitable bureaucracy that comes with that, these programs were risk averse. So rockets took a long time to develop, and the government bureaucracy was part of that problem. But what the modern entrants, what the new space players have done, and on the screen you see some examples there. The most famous example, of course, is SpaceX, which is run by Elon Musk, but there are many examples. There's Blue Origin, there's Rocket Lab, Rocket Factory Augsburg, Orbex. There's a bunch of these guys out there. And what they all do is they all chase rapid development timelines. As the definition there says, new space is a structural transformation of the space sector associated with the entry of private companies and investors, the adoption of new business models, and the reorientation of space agencies towards market-oriented policies. A completely different way of doing business. So if you think of the space economy, you're likely to think of a rocket launch for obvious reasons. And you're likely to think of the satellite that goes on the top of the rocket. And you wouldn't be wrong, but that's only one element. So the traditional way of looking at the economy is in terms of upstream and downstream segments. Before the rocket gets on the pad, It has to be developed, it has to be designed, and there is an entire industry, aerospace industry, associated with that. The satellite has to be manufactured. You need ground support equipment, you need a launch pad, you need telemetry and tracking. And if you put all of those things together and you add them all up, you have what is termed the upstream segment, because it happens before the launch. But now you sit with a satellite in orbit. It hasn't switched on yet. It's just sitting there. 10,000 kilometers above your head, 20,000, whatever it is, 400 kilometers. The moment that satellite starts to broadcast, we have the evolution of the downstream economy. Now we have space operations, people who have to keep the satellite healthy. If it's a constellation, make sure that all of them are operating. Deorbit them at the end of their lives, move them out of the way if there's space junk, all of that sort of thing. And then, of course, the big thing is products and services. When you pay your DSTV bill, a portion of that money every month goes back to Intelsat. The third segment, generally speaking, is spin-out technologies. And those are technologies that are evolved from the space industry. For example, medical innovations that have used space technology. They're no longer in the space regime, but they are part of the spin-out process. And if you look at that graphic, you might be tempted to think, because of the way that I've drawn it with the nodes on the left, you might be tempted to think that the space economy is primarily about the upstream segment. But actually, the vast majority of the money is in the products and the services. In fact, over 80% of the space economy is vested in products and services. But the great thing about rockets is that they are gatekeeping technologies. You cannot put a satellite into orbit without a rocket. So although rockets constitute a relatively minor percentage of the space economy, they are essential. And if you're working in that regime or in that area, you are always going to have business. You just have to make sure that your product is better than the competitors. ASRI is concerned, therefore, with the upstream segment. We're not concerned with the downstream. How big is the space economy? At the moment, it's estimated to be worth $500 billion annually. But it's projected to grow to $1.8 trillion by 2035. And of that portion right now, the launch services segment is worth about $14 billion. So what this tells us is that if you have a product that is worth spending money on, if you have a successful launch product, a rocket, a capability, there is a market out there. And in ASRI, we have determined that we need to capture a very small part of that market to be sustainable. Satellites, of course, are increasingly popular, and there's, in fact, explosive growth in satellite technology. The graphic there talks a little bit about satellites, the small satellite. A small satellite is anything under 500 kilograms. So 500 kilograms or less. And actually, if you look at the graphic, you will see that the average projected mass of a satellite between this year and 2032, or last year and 2032, is only about 83 kilograms, the average mass. So what this has done is it's focused attention on launch vehicles that can get small satellites into orbit. Yes, you can send a satellite on a large launch vehicle in collaboration with a whole lot of other satellites. You can send a bunch of them up. But there's a market also for small satellite launch vehicles, and that's where ASRI is interested in doing its work. In terms of our own continent, Africa is increasingly interested in satellite development, but we have one problem here, which is we don't have a launch capability. So even though we can send satellites to foreign countries for launch, there's a price to be paid for that. For one thing, it adds cost. Secondly, it restricts the orbits you're going into because you are basically hitching a ride effectively with a whole bunch of other satellites, and whatever orbit they're going into, you're going to go into that, unless you want to buy the entire rocket. But that gets very expensive. And thirdly, the problem with outsourcing launch is that you often encounter delays, and that has been a problem with some of the South African satellites that have been launched in the recent past. This is a map of the countries that have a launch capability, and it's divided into three categories: those with an advanced capability, those with an established capability, and those that are developing. And you can see where the advanced capability is shaded in gray. Effectively, the entire northern hemisphere is like that, or the north, the global north. So the United States, Russia, China, Japan, India, the whole of Europe. If they need to launch a satellite, they have the means to do it. The new entrants, there are established launch capabilities in New Zealand. The most successful small satellite launch vehicle is a New Zealand rocket. The Koreas, Iran, and then, of course, developing countries, the countries looking to develop launch include Australia, Brazil, and the United Kingdom. We have an advantage in South Africa, and the advantage is that if you want to get a satellite into polar orbit, you have to, first of all, clear your airspace, because there's air traffic everywhere. So what I've done is superimpose in the next slide the density of air traffic that is generally around and about, and it looks like that. Well, if you want to launch from South Africa, you have almost no air traffic to get out of the way, and you have very little marine traffic. And our weather is not bad either, compared to the very northern launch sites in Sweden and Norway and some of the UK islands. So we have a natural advantage. These small launches have been facilitated, they've been enabled, if you like, because they enable customers to tailor their orbits. If you want to put a small satellite on the top of a rocket, and there are two rockets there, for example, the left-hand rocket is Rocket Lab's Electron, the most successful small sat launcher, and the one on the right is ABL Systems, Space Systems RS-1. Those rockets typically carry about 300 kilograms, 300 to 500 kilograms of payload into low Earth orbit. And the main technical enablers that have enabled their development are primarily, in the last 30 years, advances in computational simulation. So you can design rockets now much more quickly because you have very powerful tools at your disposal. Modeling fluid mechanics, modeling structural loads, modeling thermal loads as well. And all of that can be done much quicker and much more cheaply than ever before. Advances in microelectronics, satellites are getting smaller. And finally, advanced manufacturing, advanced composite materials, and in some cases, additive manufacturing. On the left of your screen, you see a nice scaled diagram showing the rockets, some of the rockets that are out there, commercial rockets. And I think the one you might be most familiar with is on the far right. It's that giant rocket. It's SpaceX's Falcon 9. That will lug about 22.8 tons of payload into low Earth orbit. But the price is low. So on the right, you have a graph there of the launch price or cost per kilogram to launch on that particular rocket. And if you look at that data point, it seems to be sitting around $2,400, $2,500 US per kilogram. But there is a catch. Unless you are willing to buy the whole rocket, 22,800 kilograms, you have to share the rocket. And if you share the rocket, then according to the SpaceX website, you pay $6,000 per kilogram. And you ride along to orbit with a whole bunch of other guys' satellites. On the other end of the scale is Rocket Lab's Electron. And you might be shocked to see that the price per kilogram there is about $25,000, which is a lot more expensive. So why do people use Electron? Well, for the simple reason that it is an on-demand service. They will launch very quickly after you place the order with them, and they will take you to wherever you want to go within the capacity of the vehicle. And so we have here a case where there's a market for both of these vehicles. There's a market for Falcon 9 and there's a market for Electron. It's a little bit like the analogy between cars and buses. Right? If you want to travel from point A to point B exactly, you might want to take the car, but it costs you more. But then you can drive exactly from A to B. If you want to pay less, you can take the bus, but you might have some walking to do and you might not get to exactly where you want to go. but cars and buses are part of the economy. So we are interested in these small satellite launch vehicles. And that's where the case for a launch capability arises. I've listed there the reasons why we should pursue a South African launch capability. And there are a number of those reasons. We believe there is a business case for a sustainable launch program. There are strategic reasons. We want to be independent, data independence. We don't want to be dependent on other countries that can deny you the right to get to orbit if they don't want to host your launch, your satellite on their vehicle. There are industrial and economic reasons. We want to boost South Africa's advanced manufacturing sector. We want to drive economic growth in aerospace engineering. This is a new sector. It's not taking resources from any other. We can create employment. We can attract foreign income and generate tax revenue by launching foreign satellites on a South African vehicle. There are social advantages. We need to improve the quality of maths and science that is being taught in our schools. And a program like this can act as an incentive in that respect. There are geographic advantages, as I've explained already, where South Africa is located. And there is also legacy infrastructure from South Africa's previous launch program, which was run back in the 1980s, which was more of a military program, but there is still some legacy infrastructure available to use. All right, having made a case for launch, I want to now go into the subject of rocket science. So if you're a student here, you can get your notes out. We'll have a test in a moment or two. No, there will be no test. But it is important that we explain something about rockets so that we are familiar with the challenges, because these are crazy machines. They operate at the very edge of what is possible, and they're difficult to design. A rocket is a self-propelled machine with 4 components. It's an aerostructure, or the airframe. It has the propulsion or engine system. It has a payload and a guidance system. Most commercial launch vehicles are liquid propellant rockets, and you can see a nice little graphic there, courtesy of the folks at NASA, explaining how a rocket works. You have a tank of fuel. You have a tank of oxidizer. You pump both of those propellants into the chamber, and you ignite them, and hopefully the engine survives. And then you propel that gas at very high velocity out the back. And at that point, physics takes over, and by the law of conservation of momentum and Newton's third law, the particles go that way at high velocity, and the rocket goes that way at high velocity. And it's that simple. Trajectories can be either suborbital or orbital. You can either go on a rocket up and come straight down again. You can go into space and come straight down again. Or you can go into space and stay there, in which case you have to achieve those very high velocities that I mentioned earlier for the Intelsat and the GPS system. But chemical rockets are the only way to get to space. There is no other way at present. There's a little graphic to explain the difference between suborbital and orbital. On the left, you have the suborbital flight. Technically, a suborbital rocket must get into space and come back down again. On the right, you have to go up to get into orbit, and you have to turn and go sideways. So it's not just about going up, it's about going sideways at that very high orbital velocity. And if you do that fast enough, and at 400 kilometers you have to travel at about 28,000 kilometers per hour, you can stay in orbit. There is an Atlas V rocket. All right, so just to give you some idea, you can see on the right-hand side there's an exploded view. It's a 2-stage launch vehicle. It has an Atlas booster, which, yes, is actually based on engine technology. In fact, that actually is Russian engine technology, believe it or not, which the Americans used or bought and put onto the Atlas rocket. There's an upper stage called Centaur, and then there's the payload at the top. And what I'm going to do now is I'm going to show you a very good video from United Launch Alliance, and I've doctored the video a little bit, and I've added some graphics because we're going to build this rocket on the pad. And we're going to use the polling procedure which the engineers go through just before launch to do it. Okay, so just before launch, if you've ever watched one of these before, every guy says go, no go, etc., etc. And I'm doing this so that hopefully convey to you the complexity on one of these machines. Let's watch.
Status check to proceed with terminal count. Atlas Systems. Propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur Systems. Propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
ASGAS.
Go.
Electrical Systems. Airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight Control.
Go.
GCQ.
Go.
Op Support.
Go.
Tom.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline Monitor.
Go.
Quality.
Go.
Op Safety Manager.
Go.
ULA Safety Officer.
Go.
Vehicle System Engineer.
Go.
Anomaly Chief.
Go.
Range Coordinator.
Clear to proceed.
Launch Director.
Launch vehicle is ready to launch.
Mission Director.
You have permission to launch.
Proceeding with the count. ALC, verify T0 is set for 1247 Zulu.
Verified.
Status check.
Go Atlas. Go Centaur.
Go Silent Barker, NROL 107.
T minus 10, 9, 8, 7, 6, 5, 4, 3. We have ignition, 2, 1, and liftoff of the United Launch Alliance Atlas V rocket, carrying Silent Barker NROL 107 for the National Reconnaissance Office and the United States Space Force.
SRB chamber pressures continue to climb out. We have entered our first throttle bucket for the RD-180.
Complex machines. So even if you spend all that time and you develop the rocket, even if you get it onto the pad, you still don't really have a launch capability, because a launch capability is an entire raft of different capabilities put together. Not only do you need to develop the rocket, you also have to launch it from somewhere. So you have to have a launch pad. You have to have a spaceport. You have to be able to manage the mission planning capability. You have to do all the R&D. You have to do the supply chain. You have to build the rocket. Not easy building a rocket. You have to have a business that coordinates all of this so that you do it profitably. You need regulatory frameworks. You have to engage with governments, insurance issues. And of course, you have to have people who are skilled at doing all of this. And if you put it all together, you have what is called the launch capability. And if you take that entire system of systems, you have an ecosystem. We are concerned in ASRI with developing that ecosystem. So we are not just doing one thing. And in this talk, I'm going to address 5 of those areas: the human capital development, or the development of people skills, the launch vehicle itself, the spaceport, the R&D, and the supply chain. So something about our origins. ASRI began as ASREG, which was the Aerospace Systems Research Group, in 2009. We were started here by my colleague Jean Pitot and myself in mechanical engineering. And we built the group initially on targeted aerospace research projects at postgraduate level. And very much inspired by this new space environment that I talked about earlier. Remember that the new space era only started in the early 2000s. SpaceX, I think, was formed in 2002 or thereabouts. It only had its first successful launch in 2008. So this is all in the same sort of era. Inspired by that, we decided to develop a group. And we changed gears in 2017. We initially started a lot with hybrid rockets, and we continue to do that, but we started to look more closely at these small satellite launch vehicles. And then in 2022, we were upgraded from a research group to an institute in December 2022, and we employed our first cohort of engineers in 2023. And we are funded by the Department of Science and Innovation and, of course, the University of KwaZulu-Natal. We have aims, 3 formal aims. One is to become a global center of excellence in aerospace propulsion, to support South Africa's space engineering economy, and to develop people. We like to say in ASRI, we build rockets and we build rocket scientists, because without the people, you can do nothing. We have a range of objectives. I won't go through all of those. You can see them on the screen there. But the first of those is to support the development of a sovereign launch capability for South Africa. To put it in a nutshell, we are building a South African launch capability ecosystem. In terms of our people, the Institute has 3 directors, myself, Professor Jean Pitot, and Professor Glenn Snedden, and we employ 13 engineers, 5 senior engineers, 8 engineers, and a financial administrator. And at present, we have around 18 or 19 postgraduates at the PhD and master's level. So something about our people. As I said, we're interested in developing not just technologies, but people as well. And without that human ecosystem, sovereign launch will not happen. We estimate that we need somewhere around 50 to 60 skilled, experienced engineers to launch rockets from South Africa on a sustainable basis. And we are on our way to creating that pool of talent within ASRI. We also have what we call a talent pipeline program. And the talent pipeline program encompasses all the student-related supervision, support, and mentorship activities that happen in ASRI. And that talent pipeline also ensures a constant stream of incoming talent to help build that sustainable launch capability. There are some pictures of our people, some postgraduate students, undergraduate students in the in the process of building rockets, testing them. We prioritize community outreach. We're very aware of the fact that in a country like ours, if you propose to build a rocket program, there will be questions about that. And it's important that people firstly understand how important satellites are to their everyday lives. And secondly, that there is a business case for launch. So we do a lot of public engagements. We do a lot of STEM events. In the past year, we have reached over 1,500 school students, school pupils at schools across South Africa. We present talks, we do activities, Stomp Rocket, we build Stomp Rockets. We invite students to attend launches of the little Phoenix rockets, and we partner with the South African National Space Agency and non-governmental organizations to make that all happen. So to the technical program, ASRI has 4 main areas of work. We work in suborbital launch systems and low-altitude rockets. These are Phoenix hybrid rockets and a new sounding rocket that we're developing that will get to space on a suborbital trajectory. But the main work is focused on, in the second area, which is orbital launcher development. That's the small satellite launch vehicle, and that is Sapphire, powered by a Sapphire engine, and we call that small launch vehicle, small satellite launch vehicle, CLV, or the commercial launch vehicle. We're also active in turbomachinery research and propellants. So a word about Phoenix. Phoenix rockets are powered by hybrid motors, and this is a training program for us. This allows our engineers to learn how to design and fly rockets without dealing with very big, complicated, expensive systems. But the great thing about a hybrid rocket is it has a solid fuel and a liquid oxidizer. So it's halfway to a full liquid propellant rocket. And that's really good news because it allows us to teach or to train our personnel on how to build the flow control systems, etc., that are all part of a liquid propellant rocket. And we have made substantial incremental advances with the Phoenix rockets in the area of the aerostructures, lightweight nozzle casings, and so on. There's a picture of a Phoenix 1C rocket. It's about 5.5 meters long. And there's a cutaway in the lower diagram there, and you can see that the motor is on the left. That contains the solid fuel wax, that is the fuel for the motor. And in the middle, the big blue tank is a PVC-lined pressure vessel that houses or contains the nitrous oxide, that is the oxidizer. And then on the far right is the parachute bay and the payload bay for the Phoenix rocket. There is advanced manufacturing. I talked earlier about the supply chain. That's part of the ecosystem. So we have partnered with a company, Petrawell, who are adept at making filament wound components. So there's a nose cone being wound on the right with fiberglass, and on the left, an oxidizer tank for a Phoenix rocket being manufactured from carbon fiber. And that is very, very advanced technology. Once you've built the rocket, you have to test it. I'm going to show you a video now of the Phoenix rocket motor being tested. This is, for safety reasons, we had to drag this out onto a field far away from anybody, for safety reasons, obviously. And, well, it's on a sports field, and the groundskeeper wasn't too happy about it afterwards, but we can talk about that in a moment. As you can see, we left our mark. That's a cutaway of the Phoenix motor. As I said, it contains wax, ordinary candle wax, nothing special, and a nozzle, of course, and the nitrous oxide is injected into that and combusts with the wax to form the high-pressure gas that is then expelled through the nozzle. We have to do a whole lot of other tests before we launch one of these Phoenix rockets. So here's another little video showing the retraction of one of the umbilical connectors. So a Phoenix rocket has got fluid in it, it's got propellant in it, and you need to fuel it up when it's on the launch pad. And you can't have people near there because for safety reasons it's high pressure and it's unsafe. So here's a little test just to show you how we retract the little umbilical connector. That's a pneumatic retraction process. So once the rocket's on the pad, there's no one near it, there's no one to go and pull out the plug. It has to be done remotely and automatically. The Phoenix launch system comprises a mobile rocket launch platform, which you see in the center. All of the propellants are brought to the pad, connected up. Everything is controlled by computer. LabVIEW automatic sequencer system controls the countdown, controls the ignition. Everything is done on computer. Where do we do these launches? Well, you cannot launch a Phoenix rocket in a built-up area. These rockets can go all the way up to 18, 19, 20 kilometers. That's 6 or 7 kilometers above a commercial jet airliner. So you have to be very careful. We do all of our testing at the Denell Overberg Test Range, which is in the Western Cape. And there's a picture of that. You can see the launch pad there, LPOA. And we tend to launch these rockets out to sea so that they don't go inland, they stay away from human settlement. But this is also the launch facility where a CLV orbital launch vehicle would eventually go to low Earth orbit from. Since 2014, we have launched 6 of these Phoenix rockets, every one of them a training exercise, and 5 out of the 6 were successful. There's a little data table. You can also see the progression there. If you look at the very last line in that table, the apogee is the height that the rocket reached. When we started out with Phoenix 1A, we got to the princely height of 2,500 meters, 2.5 kilometers. We increased that with Phoenix 1B Mark 1, 11 kilometers, and then the record that we set, the African altitude record for hybrid rockets, is just under 18 kilometers. But you can see also the dry mass of the vehicle has actually decreased. So the rockets are getting more efficient. They're going higher, but they weigh less. When we go to one of these launch campaigns, we take teams. And that team process, the team building process, allows us to train the students and our personnel in how to launch rockets. And even though these are little rockets, the same principles apply to the small rockets that apply to the big rockets. So we have teams for vehicle assembly, payload and recovery, and so on. So here is the first Phoenix rocket that we ever launched. This is back in 2014.
5, 4, 3, 2.
It's a lot smaller than the Atlas V. It's only a little low-altitude rocket, but it was successful. It didn't go as high as we'd hoped. Now, if you're going to build rockets, you have to accept that sometimes you get it wrong. Not everything is a success. And we have had our share of failures. But the important thing in engineering, and not just in rocketry, but in engineering in general, is to learn from your failures so that you don't make the same mistake twice. You can judge for yourself about the mistake here.
5, 4, 3, 2, 1, 0.
Now, that was a failed launch, but actually it taught us something. It taught us a couple of important things. First of all, the cause of that failure. Are there any computer scientists here? It was a software bug. It was actually a coding mistake. We wrote the wrong code that controls the little oxidizer valve, and as soon as the motor lit, it closed. So the motor would perform beautifully, but unfortunately the rocket came back down to Earth. The other thing we learned is that hybrid rockets are really safe. Look at that scene that you see on the screen there. That launch trailer has been hit by a live rocket. If that rocket had been a solid propellant rocket or a liquid propellant rocket, there would be nothing left. All that happened in this particular case is that the nitrous oxide pressure vessel burst. And nitrous oxide, if you're not aware, is actually laughing gas. I mean, this was no laughing matter, but it's laughing gas, it just vaporizes. So there is a safety angle, and that is one of the reasons why we choose to work with hybrid rockets. Fortunately, we haven't had any failures like that again. This is the record-setting altitude flight of Phoenix 1B Mark IIR. And this is the side view of the same flight. And there are some photos taken from the top of that rocket's flight. And even though it's nowhere near space, it looks like it is, because the atmosphere is the density has dropped so low that there isn't enough air to scatter the light and make it blue. So it appears dark black almost. And that was the third highest at the time in March 2021. It was the third highest altitude achieved by any university anywhere with a hybrid rocket. 2023, another launch campaign, and this is some nice video here as well.
4, 3, 2, 1, launch.
We spin the rocket because it stabilizes the rocket, so that's intended, and then it gets to its apogee, and you can see it kind of falls over and starts to head back down again. Phoenix is great. It's a good training program, but we have our sights set on a much more high-performance vehicle, and this is called the Suborbital Test Vehicle, with the nice acronym STEVE. So STEVE is a liquid propellant rocket engine powered vehicle. So this is not a hybrid rocket motor. This is now a Sapphire engine powering a sounding rocket that we hope will get to 100 kilometers. By the way, the technical definition of space is what happens at 100 kilometers or above. So that's about the distance from Durban to Howick. That's how close space is. But it's deceptive, because to get a vehicle into space is very hard. And to get it to stay there at 28,000 kilometers an hour, you need enormous amounts of energy, chemical energy inside that vehicle. And you have to control the chemical energy. And that's what the engine does. So space is close, but space is not easy to achieve. We hope to fly STEVE in 2026, and we will keep everybody posted on that development. There's a cutaway showing STEVE. It's a liquid propellant vehicle, so it has an oxidizer tank, it has a fuel tank, and it has a payload module in addition to a single Sapphire engine at the back. But this is really what ASRI is all about. I said at the beginning that we have as our primary ambition the development of a satellite launch capability for South Africa. This is the vehicle that will achieve that. It's called, somewhat unimaginatively, a commercial launch vehicle, or CLV, until we give it a better name. It is a two-stage rocket. The first stage is powered by 9 of those Sapphire engines, and the upper stage is powered by a single engine. It's about 20 meters tall, and it is designed to carry about 200 kilograms into low Earth orbit from South Africa. It's also sized for the majority of South Africa and Africa's payloads, but it will be marketed to international customers as well once it's on the pad. So our current focus is on the Sapphire liquid rocket engine, and what I'm showing you there is just a CAD render flying around the rocket. You can see the top end is where you keep the satellite, so there's the satellite, the payload we call it, and that's the upper stage of the rocket. Below that is the engine. It's a vacuum engine, a Sapphire vacuum engine, and below that, of course, is the main fuel and oxidizer tank for the booster stage, much bigger because there are now 9 engines that have to fire all at once. And then the engine cluster at the bottom of the rocket. So we are spending a lot of time in ASRI developing Sapphire. This is the engine that will power that. And you can see a graphic of the engine on the screen there. It's a low-cost, low-complexity engine specifically designed to power CLV and, of course, the single-engine Steve suborbital rocket. It's a LOX kerosene engine, so it's liquid oxygen and effectively jet fuel. And it is driven by electrically powered pumps. It's an ablatively cooled engine, though. So the engine cooling is done by ablating a material that lines the inside of that engine. We have developed the engine. In fact, in about 6 weeks, 4 to 5 weeks' time, we're going to be doing the first hot fire test of one of these engines under pressure-fed conditions. So no pumps, but just pressure-fed Sapphire engine. And you can see there a video playing of our industrial partner, Petrowell, filament winding one of the casings for the Sapphire engine. Part of the engine is an injector. This is another very complicated piece of the engine. This is the component that takes the fuel and the oxidizer, brings it together, mixes it, atomizes the sprays, and ensures stable combustion. So we do a lot of work also on the development of injectors, and you can see in the picture there, that is an injector undergoing a cold flow test. That is liquid oxygen issuing from the little holes in the faceplate of that injector. So where are we in the Sapphire program? We started with a test engine which we called ABLE, ablative blowdown liquid engine. That's on the far left of your screen. ABLE was a prototype. It was never going to fly anywhere. It was a battleship engine, big and heavy and designed to withstand a test campaign. The next step is the Sapphire engine, which you can see in the second block. The third is, of course, manufacturing that. And we have done that now, and that is a full-scale Sapphire engine being held by one of our senior engineers. And if you take 9 of those engines and you put them together in a cluster, on the back of CLV, you have what is represented by the render on the right-hand side. And for scale, a human in the picture. This is a small rocket. ABLE was a successful test. We tested this engine back in 2021. At Overberg Test Range. It was a training engine. We needed to understand how to build liquid propellant rocket engines. And we met all our objectives in that test. And I'm going to show you a video now of this engine firing. Of course, nobody anywhere near it. We're all sitting in a blockhouse somewhere away. The engine test is controlled by computers. Everything is started up remotely. And here is the engine firing. There was a fire unit on hand to put out the fire. Of course, to test a rocket engine, you also have to have a test facility. And those containers that you see there are UKZN's mobile liquid rocket engine test facility, which we built. So actually, when you build a rocket engine, it's complex enough to build the engine. But it's also very complicated to test it because you can't afford for the engine to, it has to be tested under very strict conditions. You have to be able to control the flow rates going into the engine. You have to be able to measure the thrust, measure pressures, temperatures, and all sorts of other parameters. So again, part of the ecosystem that ASRI is developing is this ability to test. Interestingly enough, Able was at the time the second most powerful university-developed liquid rocket engine in history, as far as we're aware. And that's a little unofficial ranking of, at the time, 2021, of the most powerful liquid rocket engines developed by universities throughout the world. And you can see that UKZN is up there in second place. So part of the development part of ASRI's development plan is to develop facilities. It takes a lot of facilities to build rockets and rocket engines. We have an assembly and integration facility in the mechanical engineering discipline on Howard College campus that we've put together. This is where we build a lot of the components. We have a propellants laboratory. Propellants are the things that make rockets go. And we are very interested in novel, non-toxic monopropellants for satellite applications. In addition to what we're doing with CLV, we're also interested in on-orbit propulsion systems. And we have a team working on that. One of the things that team is looking at is gelled propellants. So normally in a liquid rocket, you have liquid fuel and liquid oxidizer. But there are certain advantages to be had by gelling those liquids and turning them into a gel. For one thing, they don't slosh around in tanks when you are launching the rocket. They are more containable if they spill. So one of our postgraduate students has just completed a project building a test rig to look at the injection of gels into a rocket combustion chamber. And you can see some high-speed footage there on the right-hand side. That's an attempt to understand what that injection process looks like. In terms of on-orbit propulsion, we are putting together a satellite thruster system because also there is commercial opportunity in that area as well. And we will use these non-toxic propellants as an advantage over the conventional hydrazine, which is usually used in rockets, which is extremely toxic, dangerous to people's health. So two of the propellants that we're looking at are HAN and ADN. And there's a little picture render on the right-hand side of a little satellite thrust. It's very small. We put the spoon in there for context and for scale. We have a subscale test facility at Mechanical Engineering, and this is used to test small liquid bipropellant rocket engines, hybrid rocket motors, small motors, not big ones, monopropellant thrusters, and ignition devices. It's a reinforced test cell, and it's run remotely by computer as well for safety. This year, we begin work on a major project, and that is our permanent liquid rocket engine test facility. And this is to be built, again, it's too big to be built here at the university. We will build that at Overberg Test Range in the Western Cape. And that consists, it's a project funded by the Department of Science and Innovation. And it consists of 3 test cells. You can see one of the Sapphire engines represented in one of those test cells. It includes a vertical test stand. So that's not a launch gantry. That's a vertical test stand where we can put a rocket, a full stack suborbital rocket, and fire the engine to see how it performs. We obviously have to supply propellants to this facility. That's a kerosene bay. There's an instrumentation bay, and around the other side is a liquid oxygen bay for the other half of the propellant mix. That facility we hope to get going in the next 3 to 6 months, and it is a funded project, as I said, by the Department of Science and Innovation. We also have a new suborbital launch gantry in development, and it's actually under construction as we speak, also at Overberg Test Range. So when you saw those pictures earlier of the Phoenix rockets launched off the trailer, that trailer we will retire, and we will move to this gantry, which is much bigger and allows us to launch bigger suborbital rockets, including the suborbital test vehicle, Steve. And that gantry is currently in development. It has a rail length of 15 meters, and it can handle a rocket up to 2.5 tons in mass. That includes the foreign NASA and European Space Agency sounding rockets. So this will enable us, we hope, to bring foreign sounding rockets to South Africa for scientific missions. So it's not just about orbital launch, we're trying to do the other things as well. Ladies and gentlemen, that brings me to the end of the talk, and I'm going to conclude now. And I want to take you back to this idea of the space launch ecosystem. ASRI as an institute is committed to developing the entire ecosystem. We are looking at the launch vehicle, but we are also interested in people. We put a lot of time and a lot of effort into developing our people. Right now in South Africa, there are probably only about 25 or so experienced liquid propellant engineers. And I would say pretty much all of them are right here at UKZN. We are looking at spaceport development, the human capital development, the supply chains. It's difficult to build rockets. We need to work with our industrial partners to do this in a variety of ways. We're looking at the R&D progress, the R&D map, if you like, to build all these components and make sure that ASRI in the end is able to conduct these tests, get a rocket on the pad, and we hope the first CLV launch vehicle by perhaps 2028 or thereabouts. Before I conclude, finally, I just want to acknowledge our stakeholders, and we have a lot of stakeholders in developing this launch capability. I first want to acknowledge the executive, the staff and students of the University of KwaZulu-Natal, of course the Department of Science and Innovation that funds the R&D aspect of our research, and the South African National Space Agency, which works with us in human capital development programs and a range of other issues as well. And also a long list of industrial partners and academic partners. I want to thank all of them for contributing to the success of ASREG and to walk the path with ASRI towards this independent satellite launch capability for South Africa. Thank you for your attention.